Hi, everyone. We are Team 9. My name is William,
I'm Yingji.
And I'm Charlie.
and we're here to talk about our diffusion guided project.
Yeah, so diffusion models have become the foundation of many modern generative AI systems as they generate images through a step-by-step denoising process. Um, and given that some of the largest applications up to date, such as Stable Diffusion and Midjourney, are driven by latent diffusion-based systems, improving its efficiency will allow these applications to gain much better real-time usage. And the current problem is that the standard DDPM requires many denoising steps, which makes inferencing incredibly slow. And we try to address this problem by reducing the cost of sampling in the diffusion model while retaining the same level of image quality. So for our dataset, we're using Cypher 10 as our preliminary training dataset for verifying correctness in code. And in total, we're using 60,000 images across 10 classes. And for our ImageNet 100 dataset, we're using it for final training, and it consists of 130,000 images spread across 100 classes. So for our data pre-processing step, we're first normalizing the data and then doing random horizontal flipping and finally encoding the image into a lower dimensional latent space with a pre-trained VAE for experimenting with LDM.
With this data, our task at hand is first to read papers to understand how the math works, then to implement that into code and extend this into some advanced techniques beyond the baseline, and finally to train for a very long time. At the core of diffusion is the forward diffusion and reverse diffusion process. Forward is where we add noise progressively. Reverse is what we want to train on denoising the original image from the noise. So there's just classic DDPM built on top of DDPM. We have DDIM, which is deterministic, and non-Markovian, which is faster at a minimal cost to accuracy. Latent DDPM using VAE to apply diffusion in a latent space. And finally, we have classifier-free guidance to allow us to generate conditional images without having to have a separate classifier.
And here are some of our results. We started training on Cypher 10. This is around 300 epochs using DDPM and CFG. As you can see, the image quality significantly improved throughout the epochs. Some of our observations are there are certain things that the model found easier to learn and some things that the model found harder. For example, clear, distinct outlines and images with high contrast areas were learned really fast and showed up earlier on in the epochs. Organic shapes, complex patterns, and images where the subject matter and background had a very similar contrast took many more epochs to learn. For example, you can look at these frogs and these birds. There's around 100 epochs between each of the sets of images. And through those 100 epochs, the clarity of the image representation, and the details of the animals themselves were much clearer after 100 epochs. After our initial training, we moved on to use ImageNet 100 as our dataset. It functions similarly to Cypher 10, where it started out more as random noise and color blobs and improved as the epochs increased. We train using both DDPM and DDIM, and currently we're still at around epoch 40, but we're continuing to train, and we will be evaluating this using FID and IS metrics. Some of our key takeaways is that early plateaus of loss imply that there might be some improvements needed in architecture and sampling methods. Additionally, we found that DDIM and latent space diffusion offered significant reductions in sampling costs without sacrificing the image quality. It looked very similar to the images created using DDPM, but it significantly reduced the training time that was needed. Additionally, noise schedule choices mattered since initial tests indicated that there were some nonlinear schedules that helped improve the convergence. Additionally, we found that CFG yielded the most significant qualitative improvements in the images themselves.
So through this project, we learned how to build an end-to-end diffusion modeling pipeline, as well as recreate some of the core functionalities of DDPM, DDIM, latent DDPM, and CFG. And through more training, we're going to see improvements also reflected within the ImageNet. And going forward, we're planning to implement diffusion transformer architecture into our current model. And as current state, our model demonstrates the feasibility and importance of building efficient diffusion models for generative AI applications through improving sampling strategies and latent space networks. And here are some of our references.
Thank
Thank
you.
Thank you.
you.